Part 2 of our mock exam, starting on multiple choice question number 10 on page 8. Got another one of these scenarios where we got four questions that go along with it. I don't like that, but 4 questions isn't so bad. Okay, it beats 7 questions or whatever we had in the last one. All this information here, guys, read through this. You see 20 centimeters, probably want to draw attention to that because we want to convert it to meters. Okay, we got a potential difference here. We got a force, an electric force here. In the end, we know that this graphite-coated sphere, graphite's a conductor. Okay, in other words, it can hold a charge. Charge can be transferred, moved around. It's attracted to the positive charge plate. Okay, that's a big deal. It's attracted to the positive charge plate. That's going to tell us that probably that it's negatively charged, right? Let's look at number 10, see what it asks. One way to give the graphite-coated sphere a negative charge is to touch it with a... Well, you got something that's neutral and you got something that's positive, they're going to balance it to be pause and pause, right? You want it to be negative, you got to touch it with something that's negative. So that's going to take us to either C or D. And if you're touching it, then we know for sure that it's going to be conduction. So the answer is going to be D for that one, for number 10. The charge on the graphite-coated sphere expressed in scientific notation is what? You know, you look at this, guys, and there's not necessarily something immediately obvious of what to do here to find the charge, but you do look at this and say, look, there's something I know how to do here, right? I got a distance between the plates. I've got a potential difference between the plates. I can find the field. Is that going to help me? I don't know, but it's something, and it's valid. So I'm going to say 3.1 times 10 to the 2 volts divided by 0.200. That gives me an electric field of 1550 volts per meter. Now, if we want to find the charge, remember that Venn diagram we do for electric fields? E is equal to KQ over R squared. E is equal to F over Q. And E is equal to delta V over delta D. The ones that apply to this situation are the bottom 2. We've already used the bottom one. Want to find the charge, let's use the middle one now. E is equal to F over Q. I got the value of E. I've got the value of F. Solve for the value of Q. And when I do that, it works out to be 5.4 times 10 to the minus 10 coulombs. 5.4 times 10 to the minus 10 coulombs. We're going to express that as 5410. Question 11. Which of the following scale diagrams is the free body diagram for the negatively charged sphere? For the free body diagram for the negatively charged sphere. Remember what it looked like, guys? You had over here on the left-hand side the negatively charged plate. You had over here the positively charged plate, and then you had this negatively charged sphere. What force do you have to have acting on this negatively charged sphere? What's the easiest one? Oddly, the one that's left out of 2 of them. Gravity. Right? Gravity's got to be acting down. So that leaves us with either A or B as our answer, right? One of the 2. Tension goes the same way in both cases. Well, the string's pulling it up that way, of course. Which way is the electric force acting on it? If it's pushed to the right or pulled to the right, then the electric force must be to the right. So the answer is going to be A for that one, right? Look at this additional information to answer the next question. The plates are now removed. The positively charged plate is replaced by a north pole of a strong magnet, and the negatively charged plate is replaced by the south pole of a strong magnet. The system is allowed to reach equilibrium. That's a big word right there. What does that mean? Equilibrium. Yeah, balance, right? Balance is stationary. As a result of the magnetic field, the negatively charged graphite-coated sphere will swing back and forth. No, it just told us it's reached equilibrium, right? Just told us, so A is not the answer. Deflected toward the north, deflected toward the south. No. Hey, you just told me Hey, Dallas, you just told me that it's stationary, okay? It's equilibrium. And if it's not attracted to one or the other, where is it going to be? When it's in equilibrium, when it's stationary, it's going to be right in the middle, right? In the end, this negative charge isn't attracted to the north or to the south. There's no force there. So it's going to eventually reach equilibrium where it's hanging straight down. These are answered. Sorry, what was that? Okay, good question. Here's our, what was the south on this side now? And the north on this side? If this is a plate over here that's a positively charged plate, it's attracted clearly to the positive plate. Okay, it's repelled by the negatively charged plate. We took those plates away. There's no electric force. But why isn't there a magnetic force in there? What do you have to have? What do you have to have for a charged particle to be affected by a magnetic field? Marker? No, it doesn't have to be accelerating. It has to be moving. Right? It has to be moving. Now, the other thing is, it actually has to be moving not parallel to the field. So in the end here, even if you think of this going back and forth, there's no force there. It's just going back and forth because it's swinging. And it's eventually, when it reaches equilibrium, it's going to come to rest midway between, right? No force between the north, because of the North Pole to South Pole, right? If it was going this way, all right, then you got, Dallas, then you got a force, right? If it's moving perpendicular to that field. "13. Two small metal spheres are fixed to insulated stands and given static charges. Here's our charges. The spheres are this far apart. We want to find the electric field caused by two charged spheres in the middle, midway between here. All right, so let's draw a picture here. Here's charge 1 that is negative 4.0 times 10 to the negative 6 coulombs. We got charge 2 over here to the right of it that is positive 2.00 times 10 to the negative 6 coulombs. We got a point midway between. These things are 0.25 meters away from the midway point. And we want to find the field right smack in the middle there at point P. First thing we got to do, guys, is not draw a free body diagram, because free body diagrams show forces, but rather draw a diagram that shows the electric field direction. The field points toward number 1. You guys remember? Field points toward negative producers. So it points towards number 1. And it also points away from number 2, because the field points away from positive producers. Now what we got to do is get both of these fields. E is equal to KQ over R squared. In both cases, E1, when you plug into numbers, works out to be 575,360. E2 works out to be 287,680 newtons per coulomb when you do the same deal with that one. You got to add them up, right? Add them up, both negatives or both positives. Doesn't matter because they're both in the same direction. The net field is equal to negative 8.63 times 10 to the 5 newtons per coulomb. They're only asking me for the magnitude, right? So the answer would be A. I'll tell you what, I think the odds of you seeing a question like this are quite high as well. Okay, we don't know anything for sure, right? Nothing for sure until after we start writing the exam. But I think the odds of seeing something that are quite high. And you know what? As much as there's a fair bit of work to a question like this, when you show everything, which I didn't do, I just kind of skipped ahead because I have the answer key in front of me. It's not a hard question, right? We can do that question. It's straightforward. We just have to go through all the work and make sure we don't make a silly mistake with it. Yeah. Sure. 14. In the electronic camera flashes, there's a capacitor, which is a device. Look, you don't even know about capacitors. They have to tell you what a capacitor is. It's a device that allows large quantities of charge to be stored. This happens to us sometimes, right? We see contexts that we don't recognize. Don't panic about that. Okay, I'll tell you, that not only do you not recognize it, nobody else in the province recognizes it either. It's nothing new to, it's something new to you, but it's something new to everybody else as well. And when that's the case, they're always going to explain it to us. They're always going to tell us about it. So you don't need to panic that, oh, we didn't learn about that, whatever. You've learned the basic concepts that you need to know. Talks about the electrical energy stored in the capacitor. It gives us a couple variables right here, potential difference. And it talks about the units for the capacitance is farads, because you've never seen that quantity before. Potential difference you've seen, you know that that's volts, right? But capacitance you hadn't. Question 14 says, which of the following combinations of coulombs, joules, and or volts is equivalent to a farad? You know, I'm not a big fan of questions like this. They give us an equation we've never seen before. It seems like an exercise in math as opposed to a physics thing. But in the end, it is what it is. Okay, we see it, we got to be prepared for it. What are the units here? Let's start off with the equation. Okay, we know the units for energy would be joules. Okay, we're trying to find what's equivalent to a farad. The half has no units with it, right? The capacitance, the unit is a farad. The unit for potential difference is volts, so it would be volts squared. So let's solve for a farad here. It ends up being joules over volts squared. Do we see that? We don't, do we? We don't. So you get joules over volts squared. That doesn't appear anywhere. We want coulombs in here somewhere, right? Got to get coulombs in here. All four of them have coulombs. So let's take a volt. We know that a volt, potential difference, is equal to energy over charge. So let's say a volt is equal to, let's see, a joule per coulomb. Let's try subbing that in and see what happens. Let's say a joule per coulomb squared, right? We're replacing volts with joules per coulomb. Yeah, let's try to make that a little bit neater, simplify it a little bit. Joule squared over coulomb squared. Let's multiply by the reciprocal. Joules times coulomb squared over joules squared. One of the joules cancels, left with coulomb squared over joules. And lo and behold, when we do that, we end up with option A here, coulomb squared per joules. So if at first it doesn't work for you, you don't get the units you want out of it, just keep plugging something else in there until eventually it works out for you. All right, let's try the next one. Love this question. Although I do think this is a tough one. I do think this is a challenge question, but I really like it. It says an electron is initially at rest at the negatively charged plate. So at this point, right here, the electron would be 0 meters per second. At the instant illustrated below, it has this much kinetic energy. So at this point, we're going to say EK is 50.0 electron volts, although in the end, we're probably going to want to end up converting that to joules, right? At any point along the path, the sum of kinetic and potential energy is what? The sum of kinetic and potential energy. Hey, listen, we got the kinetic energy at this point right here. If we have it right there, then let's just find the potential right there, add them up, and that gives us the sum and potential, sum of kinetic and potential, right? Problem is, I don't know how to find the sum of the potential energy right there. I don't even know where that is. It doesn't tell us where the electron is. It's just somewhere between the two plates. The easier way to deal with this is to say, if the energy is the same everywhere, here, and here, and here, and here, and here, and here, and here, then let's just get the total energy, kinetic and potential, at this plate. What was the kinetic energy at that plate? 0. What's the potential energy? QV. Well, we're going to say then it's 1.6 times 10 to the minus 19 times 215 volts. Get that energy, works out to be 3.44 times 10 to the negative 17 joules. We're almost done, right? That is the potential energy at the first plate. But because the kinetic is 0, it's also the sum of the kinetic and potential energy. Let's convert that to electron volts. We've done this a million times, right? Hey, you better, for next Thursday, know how to convert joules to electron volts and vice versa. Works out to be 215. Good question. Why wouldn't I use the 50 electron volts there as my kinetic energy? Let's go back to another question first. Why would they put the 50 there if I'm not going to use it? The answer to that is to throw you off, to see if you recognize that that's not the best way to tackle this question. Now, why wouldn't we use it? Okay, why isn't it important? Okay, in the end, if it's a perfectly valid number. If I could find the potential energy at that spot and add it to the 50 electron volts, that would absolutely give me 215 electron volts. It would absolutely give me the total kinetic and potential energy. The only problem is, I don't know how to find the potential energy right there. Okay, how do I find the potential energy at that point, okay, partway between the two plates, when I don't even know exactly where it is between the two plates, right? Listen, when I read this question for the very first time, I think the same thing as you. We're going to use that 215, right? But then when I try using it, it's like I can't find potential energy. I want to add kinetic and potential, but I can't find the potential energy at that point. So I got to try something else. Okay, and when I do try something else, the most logical thing that comes to mind is, oh, well, look, the kinetic is 0 here. I know the potential difference. It's easier to find the total potential energy at this plate before it's gone across, right? Before the car goes down the hill, if you think of it the way we talked about in class, rather than find the potential energy part way down the hill and add it to the kinetic. Does that make sense? All right. 15. Electron goes between two oppositely charged plates, electric field. Where's it going to go? Well, it's an electron. It's going to be repelled by the negative, and it's going to go down this way. What's the shape of that called? What's that shape? It's a parabola. Yeah, it's a parabola. It's not a circle. A charged particle goes at a circle in a magnetic field. It goes in a parabola in an electric field. That's like a rock being thrown off a cliff, right? That's projectile motion. It's exactly projectile motion, except instead of dealing with a gravitational field of 9.81, we'd be dealing with an electric field between the plates, that's all. And 4 questions that go with this DNA fingerprinting thing. Read through everything, but I'm not going to, you guys can read, so I'm not going to bother you with all of this stuff. In the end, the diagram is quite good here, okay, and it looks actually like a fairly simple diagram. 16, first question that goes with this. When molecules are turned into ions, what kind of ions are they turned into? What kind of ions do we have, positive or negative? Negative ions. It tells us they're going from the negatively charged plate to the positive plate. So if they're going towards the positive plate, they have to be negative ions. And if they've got to be negative ions, then we're having electrons being added to it to make it negative. Hey, why couldn't it be C, protons taken away? Wouldn't that make it negative? Protons taken away would make it negative, right? Except if you take protons away, it isn't going to be the same thing anymore, right? It just can't happen except in a nuclear reaction. So it's got to be. In an electrical thing, it's got to be electrons either added or taken away. 17. As an ion moves toward the positively charged plate, the magnitude of the electric force does what? Oh man, how many people are going to say it increases, or it increases as the square of the distance, or decreases? The electric force, look guys, The electric force is directly related to the charge and the electric field. It's a series of parallel plates here. The electric field is constant. We could find its value, in fact. We don't have to for that question, but we could find its value. It's not changing. If the electric field remains constant, then what do you know about the force? It's got to stay constant. B's got to be our answer. Now 4 does ask us for the electric field. So we're going to say delta V over delta D. The potential difference, if we go back to our data, was 200. And the distance between the plates is 0.100 meters. So I do that math, and it works out to be 2,000, 2.00 times 10 to the 3, which would express as 2003. '18 says, in forming a DNA fingerprint, a particular ion has been moved 3 centimeters. Probably going to want to convert that to meters if we use it. The magnitude of the charge is 2 times the elementary charge. What's the work done? What's the work? This is almost a physics 20 question, right? The work. W is equal to F times D. Don't know the force. Let's find it. Uh, 3.2 times 10 to the minus 19. Got the electric field. We just found it, right? 2,000. So then we're going to say that force times the distance that it moves between the plates, 0.03 meters. That's our answer in joules, but it's not there. So the only option we have at this point, if we've done this right, the only option we have at this point is converting it. There we go.